The prefixes D and L found in the complete name of a monosaccharide are used to identify one of two possible isomeric forms called stereoisomers. By definition, each member of a pair of stereoisomers must have the same molecular formula and the same connectivity or bonding pattern. How then do stereoisomers of the D family differ from those of the L family? Well, D and L isomers differ in the spatial arrangements of atoms in the molecule. And so even though molecules can be connected in the same way, the arrangement of their atoms in space differs, and that's what makes stereoisomers. Stereochemistry is the study of the different spatial arrangements of atoms. A general example of a pair of stereoisomers is shown on the next slide. In this example, we have a molecule with a carbon in the middle, and we have four different groups surrounding it: A, B, C, and D. This results in two possible ways to arrange the groups rather than one, and the two of them are the mirror images that you see here. Each isomer is bonded together through the exact same bonding pattern, yet the two molecules are not identical. If they were identical, they would be superimposable. That means that you can place the two molecules on top of one another, and every atom and every bond of the two will lie in the same place. If they cannot be superimposed, like these two molecules here, they are stereoisomers. These two stereoisomers have a mirror image relationship that is analogous to the mirror image relationship of the left and right hands. So even though your two hands are mirror images of each other, you cannot put a right glove on a left hand, and therefore they are enantiomers. If you were to try to take this molecule on the left, and if you were to try to superimpose it on top of this molecule, the A and the A atom would line up, so would the C. The C atom would line up as well. But the B would end up over here on top of the D, and the D here would end up on top of the B, and therefore you can see they are not superimposable upon each other. And when we have two molecules that are non-superimposable mirror images of one another, we call these enantiomers, which is a subset of stereoisomers. Molecules that can exist as enantiomers, or what we call enantiomeric forms, are called chiral molecules. The term chiral molecules simply means that as a result of the three-dimensional arrangement of the atoms, the molecule can exist in two mirror image forms, the two enantiomers. For any pair of non-superimposable mirror image carbohydrates or amino acids, one is always designated D and the other is designated L. And so some carbohydrates are designated D. These, generally speaking, are naturally occurring. These are natural sugars. And when we have an L carbohydrate, those are usually synthetic. Those are the ones that are made in laboratories. And that's why in our slides we normally see things like D-glucose, D-fructose, etc. Earlier on in this chapter, we looked at the simplest possible chiral carbohydrate known as glyceraldehyde. And we noted that the carbon in the center, or the second carbon, was bonded to four different groups, and therefore it was a chiral carbon. When we get into larger biological molecules, typically they'll have more than one chiral carbon. For example, cholesterol has 8 chiral carbons. Let's get back to the chirality in glyceraldehyde and discuss the D and L isomer. And the way that we tell the difference between the D and L isomer and glyceraldehyde is that they both have the one chiral carbon. And you can see that that chiral carbon, both of them are connected to the same things. They're connected to an aldehyde, a hydrogen, a hydroxyl, and a CH2OH. Well, then how are these molecules different? Well, you can see the difference lies in this group, the hydroxyl. And you see that in the D isomer, that the hydroxyl is pointing towards the right, and in the L isomer, the hydroxyl is pointing towards the left in glyceraldehyde. I just want to point out a trap that my students might get into sometimes. They'll say, okay, here's my carbon in the center. Is it a chiral carbon? And they'll say sometimes, no, it's not, because I have a carbon and a carbon. Remember, the chiral carbon has to be bonded to 4 different groups, not necessarily 4 different atoms. And you can see clearly that the hydrogen and the hydroxyl are different, but this aldehyde is a very different group than this CH2OH shown down here. So in fact, this is a chiral carbon because it's attached to 4 different groups. Another thing that I'll point out is that when we're designating a carbohydrate as D or L, we look at the chiral center on the farthest from the most oxidized end. So the most oxidized end is going to be the end that either has an aldehyde or a ketone on it, and we go all the way down from that, and we look at the chiral center the farthest away. Now in glyceraldehyde, it's not very complicated because there's only one chiral carbon, but when we look at something like D-glucose, we'll see more than one chiral center. And I've written the structure of D-glucose here, and how do we know that D-glucose is in fact a D sugar? Well, if we looked at the most oxidized end of the molecule, it's the end that has the aldehyde in it, right here, and I look for the chiral carbon that's the farthest away from it. So I have a chiral carbon here, 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 and here. This last carbon here, this is not a chiral carbon because this carbon is attached to 2 hydrogens, rendering it achiral. And so this being the last chiral carbon, the hydroxyl is pointing to the right, and therefore it is a D carbohydrate, and D-glucose is its name. Stereoisomers can be distinguished from one another by their different optical properties. Each member of a pair of stereoisomers will rotate plane polarized light in a different direction. This interaction with plane polarized light is called optical activity. As you would have seen way back in Introduction to Chemistry 1, white light is a form of electromagnetic radiation that consists of many different wavelengths or colors vibrating in planes that are all perpendicular to the direction of the light beam. To measure the optical properties of enantiomers, scientists use special light sources to produce monochromatic light, that is, light of a single wavelength. The monochromatic light is passed through a polarizing material, like a Polaroid lens, so that only waves in one plane can pass through. That light emerges from the lens as plane polarized light, which consists of light waves in only one plane. And so here we have an example of how an instrument called a polarimeter works. And a polarimeter is used to be able to distinguish between enantiomers. So we have our monochromatic light source here, and then it passes through this polarizing or polarized filter, which allows only one direction of the light to pass through it, and we call that plane polarized light or monochromatic light. Now what's going on here? This is actually a sample vessel. So this is actually a tube that has a solution of your organic compound in it, so your pure enantiomer. And what happens is the enantiomer is going to interact with that plane polarized light, and it is going to rotate it in a direction. It's either going to rotate it clockwise or counterclockwise. And then we used another polarizing filter mounted on a circular dial, and we rotate that until we get the maximum amount of transmitted light. And that angle is measured, and that is called the optical rotation of the molecule. Now you might be saying, well, that's interesting, and an enantiomer can rotate plane polarized light. But what's really fascinating about this and where it becomes so useful is that one enantiomer will rotate the plane polarized light in one direction, and the other enantiomer will rotate the plane polarized light in an equal amount, but in the opposite direction. One enantiomer is always going to rotate the light in a clockwise, or what we call a positive direction, and we call this the dextrorotatory isomer, or D isomer. And this is the dextrorotatory isomer. The other isomer is going to rotate the light in a counterclockwise, or a negative direction, and we call this the levorotatory isomer. And it's very important that you understand this concept right here, that under identical conditions, enantiomers will always rotate the plane polarized light to exactly the same degree, but in opposite directions. And thus, optical activity provides us with a way to distinguish between enantiomers. A scientist named Emil Fischer devised a simple way to represent the structure of stereoisomers. What we call a Fischer projection is a two-dimensional drawing of a molecule that shows a chiral carbon at the intersection of two lines, like you see here and here. The horizontal lines represent bonds projecting out of the page, and the vertical lines represent bonds that project back into the page. Here are the two enantiomers of bromochlorofluoromethane, kind of an interesting molecule they chose here. And you can see that the bromine and the chlorine are coming out towards you, right? And those are the horizontal bonds in the Fischer projection. And you can see that the vertical bonds are going back into the page because these are both on dashes. When we use Fischer projections for sugars, the aldehyde in the aldose, or the ketone group in a ketose, or the most oxidized carbon is always represented at the top. And here are three Fischer projections of some common monosaccharides. We have D-glyceraldehyde, D-glucose, and D-fructose. Remember that when we have just CHO like this is the condensed structure for an aldehyde, and therefore glyceraldehyde you can see is an aldose, as is glucose, and fructose is a ketose. You can also see the reason that they're all D sugars is because we look at the chiral carbon that's farthest away from the most oxidized end, and the hydroxyl is on the right-hand side in all of these molecules, rendering them D carbohydrates. And then finally, in Fischer projections, where we have two lines crossing like this, we have a carbon right here. So we have a carbon, 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 so on and so forth. So wherever the lines cross like that. And the reason Fischer developed the Fischer projection is because he was one of the first scientists responsible for classifying and naming all the different naturally occurring carbohydrates, and he needed a fast way to represent these molecules that have so many chiral carbons. He needed really a fast and easy and convenient way to do it, and the Fischer projection meet those criteria. When Louis Pasteur measured the specific rotation of the mixture of tartaric acid salt crystals, he observed that it was optically inactive because he had equal amounts of both the positive, the dextrorotatory, and the negative, the levorotatory enantiomer. A mixture of equal amounts of a pair of enantiomers is called a racemic mixture, or simply a racemate. Sometimes we use the prefix plus minus like this to represent a racemic mixture. In this situation, the specific rotation is 0 degrees, because the rotation caused by one enantiomer is canceled out by the opposite rotation caused by the mirror image enantiomer. When we deal with molecules that only have one chiral carbon, in that case, we can only have two possible enantiomers. However, it's really common to find molecules that have two or more chiral carbons. For example, D-glucose and D-fructose both have more than one chiral carbon. For a molecule with n number of chiral carbons, the maximum possible number of different configurations is 2 to the power of n. So let me repeat that. If you have n stereocenters, the way you calculate the number of possible stereoisomers is 2 to the power of n. So let's say we're talking about cholesterol, which has 8 chiral centers. We would say the number of possible stereoisomers is 2 to the power of 8, which is 256. That's a lot of possible stereoisomers. Now remember that this formula predicts the maximum number of configurations. There can actually be fewer than that. Another definition you should be familiar with is diastereomers. And diastereomers are simply a pair of stereoisomers having 2 or more chiral centers, but they aren't enantiomers. And then finally, you should also know what a meso compound is. And a meso compound is a compound with 2 or more chiral carbon atoms and an internal plane of symmetry that causes it to be optically inactive. In 1891, Emil Fischer devised a nomenclature system that would allow scientists to distinguish between enantiomers. Fischer knew that the two enantiomers of glyceraldehyde rotated plane polarized light in opposite directions, but he did not have the sophisticated tools needed to make an absolute connection between the structure and the direction of the plane polarized light. He simply decided that the plus enantiomer would be the one with the hydroxyl group of the chiral carbon on the right, and he called it D-glyceraldehyde. It was his choice. The enantiomer that rotated plane polarized light in the minus or levorotatory or opposite direction, he just called it L-glyceraldehyde. While specific rotation is an experimental value that must be measured, The D and L designations of all other monosaccharides are determined by the comparison of the structures with D and L glyceraldehyde. Sugars with more than 3 carbons, like D-glucose and D-fructose, shown here, will have more than one chiral carbon. For example, glucose has 4 chiral carbons. 1, 2, 3, 4. Fructose has 3. 1, 2, and 3. By convention, it is the position of the hydroxyl group on the chiral carbon farthest from the carbonyl group, or the most oxidized end of the molecule, these ones here highlighted in pink, that determines whether a monosaccharide is in the D or L configuration. One way to be sure you are considering the correct chiral carbon is to number the carbon chain, giving the carbonyl group the lowest possible number, as is shown here in blue. The chiral carbon with the highest number, in this case 5 and in this case 5 as well, is used to determine whether the molecule has the D or L configuration. If the hydroxyl group is on the right, the molecule is in the D configuration. And this is on the right, and this hydroxyl is on the right, and therefore these are both D carbohydrates. If the hydroxyl group were on the left, the molecule would have the L configuration. Again, almost all carbohydrates in living systems that are naturally occurring, of course, are members of the D family.